Hello friends. Here we are starting with the advanced actor-critic algorithm, or just A2C for short. Now before we get into the details, let's take a step back and think about what this algorithm is actually doing. A2C is one of the popular actor-critic methods in reinforcement learning. It builds on the idea that we can combine two different roles, one that decides what to do and one that evaluates how good those decisions are. So we have got an actor and we have got a critic. Now, A2C itself is basically the synchronized version of A3C, which is the asynchronous one. Instead of running multiple agents in parallel and updating them at different times, A2C keeps the training steps in sync, and this makes the training process a bit more predictable and stable. So you might wonder why combine these roles at all. The actor by itself can be unstable, especially when the feedback is noisy or sparse. The critic helps smooth that out by estimating how good a state is, so the actor doesn't overreact to a single reward or best step. So with A2C, you get a policy that improves over time, but without the wide fluctuations. And now, let's break down the core parts of A2C, and I will walk you through how they connect to each other. And here we have the actor network. Its job is to learn a policy. That's the part that picks an action given the current state. So for every situation the agent finds itself in, the actor outputs a probability distribution over the possible actions. In discrete environments like Atari games, this might be a softmax or button progress. In continuous settings, it could be the parameters of a Gaussian. Right below that, we have got a critic network. This one estimates the value of a given state, basically how much total reward we expect to collect from that state if we follow the current policy. It doesn't tell us what to do, but it gives us a sense of how promising each state is. And the critic plays an important role in guiding the actor during training. It gives a signal about whether a chosen action led to a better or worse result than expected. And there is the advantage function. This is where things get a bit more precise. Instead of just using the raw return or the value function directly, the advantage function helps us focus on the relative value of an action. So we ask, was this action better than what the critic thought would happen? And the formula looks like this. You can see A of S and A equals Q of S and A minus V of S. But since we don't usually estimate Q directly in A2C, we approximate it using a one-step return. The immediate reward plus the discounted value of the next state minus the value of the current state. So R plus gamma V of S prime minus V of S. Okay. Down here you can see the four main pieces of experience the agent deals with: the current state, the action it takes, the reward it gets, and the next state it ends up in. These are the basic ingredients for computing advantage and updating the networks. Now coming back to the actor and the critic, let's go a bit deeper. The actor is what learns to make decisions. It looks at the state and says, here's what I think we should do. It is trained using the advantage signal, and the goal is to choose actions that lead to high returns. It can handle both discrete and continuous actions depending on how you design it. And during training, it's rewarded when the actual outcome is better than expected and penalized when it is worse. The critic, on the other hand, works in the background. It estimates how good the current state is. It doesn't propose actions, it just evaluates them. And by doing that, it provides a baseline. And having a baseline is useful because it reduces variance in the training signal. Without the critic, the policy updates would be noisier and less stable. It also helps the agent learn faster by providing some structure in how rewards are interpreted. And okay, we'll talk about how the advantage function works, because this is where A2C really tightens things up compared to simpler possibility methods. So here's a question we are asking: when the agent takes an action in a given state, how much better was that action compared to what we usually expect in that situation? That's what the advantage function tells us. It is not just about whether the action gave us a reward, it is about how much better or worse it was than the average action the might have taken in that same state. And mathematically, the advantage is defined as the difference between the q value and the v value. That's a of s at a equals q of s, a minus v of s. But in practice, in A2C, we don't usually estimate Q directly. Instead, we use something called one-step TD approximation. That means we say, okay, let's take the reward we just got at discounted value of the next state and subtract the value of the current state. So R plus gamma times V of S prime minus V of S. That gives us an estimate of how good that action was. And algorithm time here. First comes initialization. We randomly set up the weights for both the actor and the critic networks. The actor is the one that's going to learn the policy, and the critic is going to estimate how good each state is. We also choose learning rates for both of them, which might be different, and we set discounted factor gamma. If we are doing n-step returns, we also choose the value of n here. Once everything is initialized, we start collecting experience, and at each time step, the agent observes the current state. Then it uses actor to sample an action from the policy distribution. That action gets executed in the environment. The environment then responds with a reward to the next state and a done flag if the episode ends. We store all of this, the state, action, reward, next state, and done signal in a buffer. Once the buffer holds n step, we move to the next phase. And advantage estimation. This is where we start pulling together what the critic thinks and what actually happened. For each point in the trajectory we collected, we compute the value of the current state using the critic. Then we calculate the return using n-step bootstrapping. That means we sum up the rewards discounted at each step and then add in the value of the final state, also discounted. And finally, we subtract the current value estimate to get the advantage. So advantage equals returns minus value estimate. And now that we have the advantage values, we can update the networks. Let's start with the actor. The idea is to shift the policy in the direction of better actions. We do this using the gradient of the log probability of the action scaled by the advantage. The larger the advantage, the more we want to reinforce that action. The policy parameters are then nudged in that direction. On the critic side, we are trying to make its value estimates more accurate. So we take the square difference between the actual return and the critic's estimate, and we update the critic weight to minimize that. Sometimes we also add an entropy bonus to the policy update. That just means we are encouraging the policy to stay a bit random, so the agent keeps exploring. If you push the entropy too low, the policy can get stuck in a suboptimal behavior early on. So we usually tune this with a coefficient which we call beta. And once we are done with these updates, we go back to collecting experience and repeat. We keep looping through this process. What are the experience collection, advantage estimation, network updates, until we reach convergence or hit a predefined number of iterations. And let's pause for a second and think about what makes A2C appealing. One big thing is that using the advanced function helps reduce the variance in policy gradient updates. That makes the training more stable. The synchronous update mechanism also helps here, especially compared to older asynchronous versions like A3C. Another point is sample efficiency. Because we are estimating values with the critic and using that to guide the actor, we get more value out of each trajectory we collect. We are not just throwing away information after one use. Also, A2C gives us a decent balance between exploration and exploitation. With the entropy term in the policy loss, we can control how random the agent's actions are. This prevents the policy from becoming too confident in a bad solution early on. And last thing before we move on, some practical notes you will want to keep in mind. First, learning rates. The actor and critic don't always benefit from the same rate, so it's worth tuning them separately. And second, the network architecture. In some cases, the actor and critic might share a few layers, but in other cases, keeping them separate gives better results. It really depends on the task. Third, the value of n in n-step returns matters. If n is too small, you don't get much look ahead. If it is too big, you introduce more variance. So there is a trade-off. Usually, people experiment to find what works best. And finally, entropy regularization. If the entropy coefficient is too high, the agent will act too randomly and struggle to learn. If it is too low, the policy might settle too quickly. So again, this needs to be adjusted depending on your environments. Okay, and table. So at this point, it's useful to stop and ask how does A2C stack up against other common reinforcement learning algorithms? What makes it different and when should we consider using it? And first, reinforce is here. That one is a basic post-gradient method, It's fully on policy and uses Monte Carlo returns. It is simple and easy to implement, but it doesn't really reduce variance well. It does have a baseline, but it is pretty limited on what it can handle. And because of that, sample efficiency is quite low. It takes a lot of experience to learn anything useful, and in terms of stability, it is not great. And DQN is on the other end of the spectrum. That's a value-based method. It uses a Q function and selects actions with an epsilon graded policy, which is deterministic with some randomness injecting during exploration. And DQN is known for being efficient with samples, especially because of experience replay. But it struggles with continuous action spaces. You can make it work, but it gets messy fast. And its stability depends on techniques like target networks to keep the training from blowing up. PPU is a more modern actor-critic method, like A2C. It also uses the advanced function, but it adds scripting to await large, unstable policy updates. That's one of the reasons it's considered more stable overall. And it handles continuous actions like A2C, but is generally a bit more robust in practice. It also tends to be more sample efficient than A2C, especially in larger environments. And A2C sits somewhere in the middle. It gives you a decent balance. It's an actor-critic method, so it has that dual structure of policy and value networks. And it uses synchronous updates and it supports continuous action spaces and you will have to implement that manually depending on the framework. In terms of stability, it's okay, not as stable as PPO, but more predictable than reinforce. So depending on the environment and your needs, A2C might be a solid starting point before you reach for something more complex. And here's some variants and extensions. Okay, first up is A3C. That's a asynchronous version. The idea here is to run multiple copies of the agent in parallel and let them update a shared model independently. This helps with exploration because each agent might encounter different experiences, but it comes with its own challenges, mostly around coordination and shared memory. And A2C with generalized attention estimation, what it does is combine multiple step returns with exponential weighting. This helps balance bias and variance more effectively. So instead of giving equal weight to all time steps, it discounts further out returns more aggressively. That usually leads to smoother and more reliable updates, especially in environments with noisy rewards. And Actor-Critic with experience play, that one brings in experience play, something A2C doesn't do by default. And since Actor-Critic methods are usually on policy, it is not easy to reuse past data. But this method tries to make it work using opposite corrections. This lets it learn from older experiences without introducing instability, and it is a more advanced variant, but it can improve sample efficiency if implemented properly. And finally, soft actor critic. This is not exactly a variant of A2C, but it is worth mentioning here. Soft Actor-Critic is off-policy and includes entropy maximization directly in its objective. That helps the agent keep exploring throughout training. It works especially well in continuous control problems like robotics. So if you are working in that space, Soft Actor-Critic might be a better tool.